So, so let me just recall our theorem. Automorphism plus some additional property conditions, which is infinite and not a conjugacy class, not a conjugacy. Then there exists an action, the centralizer of phi preserves an F entry. So in the remaining, in the second part of my talk, I want to explain what is the how do you construct such an F entry? And for that, I want to explain first to explain how do you construct a tree for a simpler case, which is the case of a geometric automorphism. Geometric case. So recall that any if you take sigma, a compact surface, with one boundary component, if you take an element x of sigma, then any homeomorphism sigma fixing x induces an automorphism. Fn. So let me explain the construction of the tree in this case. And the construction was already known from work of Thurston. So this is a theorem which is due to Nielsen and Thurston, which says that if you take F to be an automorphism of pi1 sigma preserving x, represented which represents the homeo F, there exists a decomposition the surface sigma by cutting along closed curves. So if you write, so if I represent my surface sigma as follows, you can find closed curves alpha 1, alpha 2, and alpha 3. This decomposition is preserved by centralizer of your homeomorphism up to homotopy. So meaning that any homomorphism in the centralizer of F and the homotopy class of all the subsurfaces that you obtain by cutting along sigma along the alpha i's. So you obtain subsurfaces which I called sigma 1, sigma 2, and sigma 3. And in fact, all the dynamics of the homomorphism F because and such that for every I in 1, 2, 3. So if you look at the restriction of F into the subsurface sigma I, one of the following holds. Either this restriction is homotopic to the identity, or else the centralizer of F, sigma I, is isomorphic to an infinite cyclic group generated by the element F. So what you obtain is a decomposition of your surface, which is well suited for, which is completely and captures the dynamics of F. So that either it encaptures or else the others which have a chaotic way that the centralizer should be very small, namely it should be restricted to the element itself. And now out of this decomposition of the surface, you obtain an action on the tree as follows. So I just build once again my surface. Sigma 3, sigma 2. I assume that the universal cover is isometric to H2. And for H2, I will look at lifts of the closed curves alpha I. 1, alpha 2, alpha 3. They are disjoint because the representatives in the quotient are disjoint. But you can also look at the all the orbits of the lifts of alpha I by elements of the fundamental group of the surface. Then you can also look at G alpha 1 hat, where G is in the fundamental group of the surface. So remember that it acts on the H2 by deck transformations, and it sends the lift of alpha 1 to G sends the lift of alpha 1 to a lift of alpha to another lift of alpha 1. And you can do that for every alpha i's. So what you obtain are completely disjoint alpha. And you do that for every element of the fundamental group. So what you obtain are closed, are disjoint B-infinite geodesics, which cuts the hyperplane H2 onto a large number of connected components. And what you do is that for each connected component, you can construct a tree as follows. Its vertices are points uh, are the 1 point for each connected component. And 2 points are adjacent when they're separated by a B-infinite geodesic representing one of the alpha i's. And what you obtain is a tree. The resulting graph is a tree, which depends on the alpha i's. And since we look at all the orbits of all the alpha i's by elements of the fundamental group, it comes equipped with an action of the fundamental group, and thus an action of your free group. And there, the stabilizer of a point is isomorphic to the fundamental group of one of the subsurfaces. And there, the stabilizer of an edge is isomorphic to Z, and it is isomorphic to the fundamental group of one of the closed curve that you started with. So now you obtain a decomposition. You obtain an FN tree which encaptures the dynamics of the automorphism induced by the homeomorphism F. Namely, on the stabilizer of each vertex, it either acts completely trivially because F is homotopic to the identity, or else it has a completely chaotic dynamics, and the centralizer of the restriction of F to the stabilizer of the vertex is isomorphic to Z. And this is kind of this decomposition completely depends on the way that your homeomorphism acts on your surface. And this is how we will construct a decomposition, an FN tree on which is preserved by the centralizer, by constructing FN trees which are closely linked with the dynamics of the automorphism. So our goal is to construct an FN tree which encaptures dynamics of the automorphism that you started with. So first, I will consider, in order to do that, since remember for the geometric case, we obtain subsurfaces where the homomorphism acts trivially, namely is homotopic to the identity. I will start with the subgroup, the fixed subgroup of phi, which is the set of all elements of Fn such that phi of G is trivial. So this group, it is a canonical subgroup associated with phi because it in the sense that it is preserved by the centralizer of phi. And in fact, our goal, as in the geometric case, it is to construct an FN tree where fixed phi is the stabilizer of a point, is the stabilizer of a vertex. trees that we will construct are in some restricted families. The trees we construct have either trivial or cyclic stabilizer. Or cyclic edge. The stabilizer of an edge is either cyclic or trivial. And so first, there will be different cases according to whether you can find an FN tree which is fixed, where fixed phi stabilizes a point, and which have trivial or cyclic edge stabilizer. So we'll need some definitions. An FN tree relative to fixed phi is an FN tree where fixed phi fixes a point. N tree relative to fixed phi is free if all edge stabilizers are trivial. And it is cyclic if all edge stabilizers are cyclic. So the construction of the FN trees will be divided into several cases. The first one is that there does not exist any free FN tree relative to fixed phi. So this case can happen in several places. For example, for the case where phi represents a geometric automorphism, this is because phi preserves the element of a geometric automorphism. So it represents a homeomorphism of the surface. And this is because phi preserves the element of the fundamental group of the surface, representing the boundary component. And the boundary component of the surface can never act freely, acts on an FN tree with trivial edge stabilizers. Another example comes from twist automorphism that I explained above. So I recall it is an automorphism which sends each xi to itself if I is strictly less than n, and it sends xn to xng, where g is contained in x1, xn. So what is the fixed subgroup of this automorphism? So it is generated by all the xi's whose index is at most n minus 1, but it also contains x1 g xn g xn minus 1. So a simple computation tells you that it fixes this element. And in fact, the fixed subgroups of phi is generated by these elements. So the first n minus 1 elements generate the free factor of corank 1. So any free factor which contains fixed phi will be of rank n, and the only free factor which is of rank n is the whole group itself. So there does not exist such an FN tree. An FN tree, a free FN tree relative to fixed phi. So in that case, it is a theorem which is due to Girardel and Leavitt, which tells you that there exists a cyclic FN tree relative to fixed phi. And in fact, it is completely canonical because it is automatically preserved by not only the centralizer of phi, but also the stabilizer of the group fixed phi, the stabilizer in haute FN. And what's quite remarkable is that they give a complete description of the vertex stabilizers. If you take a vertex of this tree, the stabilizer of V will be either isomorphic to fixed phi, the stabilizer of V will be isomorphic to the fundamental group of a surface. So the picture that you need to have in mind is the following. So the quotient of Fn of the tree by Fn will look like just as follows. So we will have vertices whose vertex stabilizer will be isomorphic to fixed phi, and all the other vertices will be isomorphic to fundamental group of the surface. Where so each edge group, the stabilizer of each vertex is isomorphic to Z, and it embeds in the boundary component of the surface. So you can have several edges, which is adjacent to the boundary component of the surface, and you can have other surfaces. Well, but what you need to have in mind is this case is very close to the geometric case because all the tree you obtain are either composed of a fundamental group of surfaces, so a case that you really understand very well, or else it is a fixed subgroup of phi and you understand it completely also. So you see that the most difficult case is the case where case 2, there exist 3 FN trees relative to fixed phi. So the problem is there can be infinitely many. It is possible that there are infinitely many FN trees, free FN trees relative to fixed fee. And the point is, we will try to find a canonical FN tree relative to fixed fee. So the way we will do this is through three factors. So remember that if you start with a free product decomposition, you can construct FN trees, which is associated with this free product decomposition. So we'll first look at trees of the form TAB, which are where fixed fee fixes a point. So you see, now the first case was we try to find trees where fixed fee is not contained, does not fix any free FN trees. The second case is to find free FN trees which are closely related to free product decomposition. And in fact, is that, for instance, if fixed fee is contained in a free factor A rank n-1, and A is minimal for this property, and A is minimal, meaning that fixed fee is not contained in any proper free factor, then there exists a canonical free product decomposition. So maybe I can give you an easy example. So you look at the automorphism of the free group of rank 3 generated by A, B, and C. Which sends A to A, B to B, and it sends C to B, C, B minus 1. Then the fixed subgroup of phi, it is generated by A and B. So it is a free factor of rank n-1. And we have a canonical free product decomposition, which is the following. Fn is equal to AB, the free product of the group generated by AB and the group generated by C. And you can easily show that this free product decomposition is canonical. It's canonical, meaning that the centralizer phi preserves the free factor AB and the free factor C. And so, in particular, the centralizer of phi will act and will preserve the Basser tree associated with AB and the Basser tree associated with C, of AB and C. So you see that in some cases, you can find a canonical free product decomposition, and therefore you can find a canonical action on a tree, on a canonical Fn tree, which is preserved by the centralizer of phi. And now there is the remaining, the last case is the remaining one. So the last case is following. There exists free Fn trees relative to fixed phi, and there does not exist free product decomposition preserved by the centralizer of phi. So this case is just, for instance, the Fibonacci automorphism that we discussed in the first part of the talk. So this case is the trickiest. And what we do is, well, even though we have infinitely many Fn trees relative to fixed phi, we can look at the restricted action of the centralizer of phi on the set of all Fn trees relative to fixed phi, of all three Fn trees relative to fixed phi. We will give a graph structure out of this set, where two trees are adjacent plus a graph structure. Where two trees are adjacent, whenever there exists, you can obtain T prime is obtained by collapsing some edges. So what do I mean by that? So if a fundamental tree, if a fundamental domain of the tree T is, for instance, a segment where the stabilizer of this vertex is A, the stabilizer of this vertex is B, and the stabilizer of this vertex is C. And T prime is a fundamental domain is just one edge where the stabilizer of first vertex is AB and the stabilizer of the second vertex is C. Then you see that you can obtain T prime from T by collapsing the edge of T between the stabilizer of A and the stabilizer of B. This is what I mean by obtain from T by collapsing some edges. So collapse this edge. And so now we have an action of the centralizer of phi on a graph. And what's very interesting is the following theorem. Which is due in this form to Gödel and Orbe. Which tells you that this graph is Gromov hyperbolic. Meaning that it satisfies a strong negative curvature hypothesis. A strong negative curvature property. Why is it interesting? It's because from this hyperbolicity, you have a complete understanding of the isometry group of a hyperbolic graph. So in fact, it's a theorem which is due to Gromov, which classifies all the isometries of a possible hyperbolic graph, and more generally, a Gromov hyperbolic metric space. And what we prove is that proposition, the action of phi on this set of f entries relative to fixed phi is what we call loxodromic. So what does that mean? So if this disk represents the set of all f entries of three f entries, I forgot the three hypotheses, the set of all three f entries relative to fixed phi, you can find in this disk 2 points . which we call delta minus of phi and delta plus of phi, such that if you take any point which is not delta plus of phi or delta minus of phi, if you take this point, and if you look at the orbit of phi of this point x under iteration of phi, it will converge to delta plus of phi. This is under iteration of phi. And if you iterate by phi minus 1, it will converge to delta minus of phi. This is under iteration of phi minus 1. And this is true for every point x. So in fact, what you obtain is the following. You obtain two canonical points which are delta plus of phi and delta minus of phi. These points, and this point will be linked with three FN trees relative to fixed phi. They are preserved and they are preserved. Centralizer phi. So you obtain 2 points, delta plus and delta minus of phi, which corresponds morally to almost 3 FN trees relative to fixed phi. And since they are canonical for the dynamical action of phi, they will be preserved by the centralizer of phi. So for the last 3 minutes, I will just sketch a proof of this proposition. So this is because otherwise, if phi is not loxodromic, you will find another element in the centralizer of phi, which will be loxodromic. So this is kind of the definition, this kind of follow from the way we construct the action. And because we are in the first 2 cases, in fact, deals with the case where there does not exist an element in the centralizer which is loxodromic. So the third case, necessarily we have a loxodromic element. So it will also have maybe not this one, delta plus of psi and delta minus of psi. And psi will have also have these dynamics where every point is attracted to delta plus of psi. But this delta plus and delta minus of psi will be preserved by phi. Of psi, delta minus of psi will be also preserved by phi. Because phi commutes with psi. And what we show is that this is not possible because it will imply that fixed phi is larger than larger than expected. So what do I mean by that? It's because we have a complete description of what can be the possible delta plus and delta minus of psi. And if phi preserves both of these points, and if they are not itself, if it's not the attractive and repelling point for phi itself, it will force it to fix a lot of FN trees relative to fixed phi. And the fact that it preserves a lot of such trees will imply that it has a large fixed subgroup, and in fact a fixed subgroup which is not contained in any stabilizer, the vertex stabilizer of any point. And this will contradict the fact that we are in case that fixed phi fixes a point in an FN tree, in a free FN tree. So I will stop here, and thank you very much for your attention.